Hello everyone, my name is Hian. I usually go by Siv, and today I'll be presenting my final project for our class Introduction to Remote Sensing, which focuses on detecting the hurricane-driven water quality changes in Tampa Bay, Florida. Um, so why look at the Tampa Bay and why look at the turbidity? The hurricane can dramatically disturb the water quality by resuspending the sediments and increasing the water storm runoff and pushing the pollutant into the shallow estuaries. And Tampa Bay is an ideal case because it is large, shallow, and ecologically sensitive. The Hurricane Helene and Milton struck just like weeks apart, which make 2024 a powerful natural experiment. And instead of relying on the institute sampling, which is quite limited in the coverage and time, so remote sensing gives us a synoptic and repeatable way to monitor turbidity at the landscape scale. So Tampa Bay is one of the largest estuaries in the Florida. It connects to the Gulf of Mexico and or Gulf of America now. It's received fresh water from several rivers, including the Hillsborough, Alafia, and Manatee's rivers. Because it is shallow and enclosed, the bay responds strongly to the sediments disturbance. Even with moderate storm, it can cause the rapid changes in turbidity. But with two hurricanes back to back, we would expect to see much more dramatic system-wide impact. My research question is pretty straightforward. I just want to examine how did the hurricanes Helene and Milton influence the turbidity and the sedimentary suspension across the Tampa Bay. For data, I use Landsat 8 and 9 operational land imager level 2 surface reflectance products, which already included the atmospheric correction, so I could just move directly into calculating a spectral index. So I selected two key dates: the pre-hurricane, which was in May 11, 2024. It's one of the time where it has low cloud coverage, and then for the post hurricanes I picked October 18, 2024. It's pretty much it's 4 days right after the Hurricane Milton, and it's really fortunate that that time it has low cloud coverage. This data is both of them capture the condition before and after the storm impact accumulated. For the spectral band, I use green, the band 3, red for band 4, and near infrared range for band 5. They specifically use it for the NDWI testing for the water. For reprocessing, my workflow was fairly minimal because the Landsat Level 2 surface reflectant product is already atmospherically corrected. So first, I would just clip each scene to Tampa Bay boundary by using an area of interest AOI subset. Then I created a stack of band layers so that all necessary bands were aligned. And then next, I just calculated the NDWI using the green and near infrared bands to enhance the water features, because I will use the NDWI layers to generate a water and non-water mask. And then I applied the band mask clipping into to remove the land pixels. And after isolating the only the water pixels, I computed the NDTI using the red and green bands. And finally, I applied the colorams, classifying the turbidity intensity, and then producing the map histograms and for to comparing the pre and post hurricane condition. I use NDTI for this analysis for of turbidity by calculating the red minus green divided by the red plus the green. So I choose this NDTI because previous studies have shown that the NDTI is efficient in detecting the turbidities, and also the sediment detection in the coastal environments. It relies on the spectral relationship between the red and the green bands, which respond strongly to the variation in suspended sediments. Um, Also for the NDTI value, it's also indicate that when there's a high NDTI, it leads to higher turbidity and vice versa. The NDTI is especially useful in the estuaries like the Tampa Bay, where the water color can shift dramatically after major like storm events. Before calculating the NDTI, I examined the green band reflectant first because this is what we learned in one of our lab in class. Um, in the pre-hurricane image, the water appeared like darker and even more uniform. This typically like signal that there's a clear water with like a minimal sediment loaded. Um, but in the post-hurricane, the image we start to see there's like a bright green, yellow, and even reddish tone. This indicate that there's the shallow area, the sediment plumes, and the runoff from the inland watershed. Um, the green band alone already suggests there's an increase of turbidity or high algae presence after the Helene and Milton hurricanes. And now we move into the NDTI value. This is where the impact of the hurricanes Helene and Milton become extremely clear. Let's start with the pre-hurricane NDTI map first. So before the storm, most of the Tampa Bay show moderate or low turbidity. The Tampa uh, the Tampa Bay appear relatively stable with the clear water concentrated toward the central and an outer portion of the estuaries. The high turbidity pocket are minimal and mostly restricted to a very shallow near the shore area, and it is expected for like large estuaries during springtime. The conditions are like calmer and with like a lower runoff and fewer disturbances. When we shifted to the post-hurricane NDTI map, the changes is like dramatic. Like almost immediately we can see like there's like a large region lighting up with high NDTI values. This corresponds to the significant increase in suspended sediments. The bright yellow, orange, and red tones indicated there's a heavy disturbed water, and they appear all, like across almost like entire system, not just like near the shorelines. So one of the most notable pattern is how like far the sediments like plums travels. Instead of remaining in like a localized near the river mouth or shallow bank, its plumb extended to like a central bay and even toward like the offshore areas near the mouth of the estuaries. This suggests that there's a strong winds driving mixing with the tidal currents that disturbing the sediment and widely than like usual. Another key is the clustering of the 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 pattern that strongly suggests the elevated runoff following the heavy rainfall that brought by the hurricanes. And those rivers are very likely to carrying a large pulse of like suspended materials into the system, which the storm energy then like dispersed. Um, the side-by-side comparison also highlight these changes even more strongly. The turbidity zone expanded to outwards from the coastline into the central bay, which suggests that there's a both sedimentary suspension from the winds and transport of the riverborne material downstream following the heavy rainfall. So overall, the contrast between these two maps highlight the system-wide transformation. The bay shift from relatively clear and stable conditions in May to widespread disturbance in October right after the storm. This also reinforced the idea of like consecutive hurricanes not only increase stability but can sustain the elevated sediment loaded for weeks or even months after the event. Um, So this NDTI map visually confirm what literatures have been described about like the hurricane impact, the rapid resuspension and increased mixing, that amplifying the sediment transport across the coastal estuaries. To quantify the visual pattern, I also generate the histograms. The pre-storm distribution is narrow and centered on more like a negative NDTI value that indicating there's a clear water. And but for the post in this curve, we see that there's a spread of outward and shift toward like zero and even more lean toward like more positive values as well. This kind of signal that there's a higher turbidity and greater spatial variation. This broaden the distribution is also strong numeric indicator of the storm induced disturbance. The numbers, it's the same thing, also reinforce the same thing, the visual and the histograms finding. If you look at the standard deviation, you see that's increased from 0.18 to 0.26, meaning that the turbidity has become more spatial variables. And if we look at the means as well, they also have like some slight increase. Together, this metric confirmed that the hurricanes elevated the turbidity throughout the bay. Classify the turbidity area also show the most dramatic shift. If we look at the very low turbidity, it shrank for about 480 square kilometer. And if we look at the moderate turbidity, it surged from less than 1 kilometer to over 250 square kilometers. And for high turbidity, the same thing, it expanded system wide. This means that the bay moved into like disturbed state and with elevated turbidity dominating the entire system following the storms. The result clearly showed that the hurricanes Helene and Milton caused major increase in turbidity across Tampa Bay. The shift from mostly low to widespread moderate and then to high NDTI value suggests that's a strong sedimentary suspension from the wind and waves, which is expected in like a shallow estuaries during the extreme storms. And the high turbidity around the river mouth also indicating there's a increased runoff carrying the sediments and pollutant into the bay after the heavy rainfall. The broader NDTI distributions and higher standard deviation also reinforce that water quality has become more variable and disturbed after the storms. And this changes much that previous study describing about the hurricane impacts, that there's a rapid mixing of bottom sediment disturbance and the movement of the suspended material throughout the systems. So overall, the Landsat 8 and 9 proven and effective for detecting the short-term water quality changes in the Tampa Bay. Even with the moderate resolution, they provide clear evidence of system-wide turbidity increase, showing that satellite image remote sensing is a reliable tool for assessing the post-storm water quality in the coastal environment. This is the last slide of my presentation. Thank you so much for listening. Thank you.